What's your situation?
So for problem 4, it's dx1 minus tx1 minus 18x.
So say that one more time.
10x.
Okay, I heard T for a second. 10x1.
10x1.
Cool. And let me before you say it, let me guess. I'm guessing that dx dt is going to be 6x1 minus 11x2. Interesting. Mine is not exactly the same as that, but it is almost the same. In what I have written here, my 18 and my 6 are switched. Interesting. And what are your initial conditions?
X1 equals 3.
Okay, and x2 equals 3. Mine are switched as well. It's kind of neat. So I bet a lot of stuff comes out to be pretty much the same as what I did, but maybe a little bit different. Okay, and of course, this is Co-17C. Today is November 14th of 2023. All right, so here's the situation. Let me just say a couple things before we solve the problem. So if we were just asked to classify whether our equilibrium was a saddle, a stable node, an unstable node, a spiral, whatever, all we would need to do is look at the eigenvalues or even look at the trace and determinant. So I want to talk about the trace determinant for just 1 minute. So our matrix here would be the matrix 10, negative 18, 6, negative 11. The trace is equal to 10 plus negative 11, which is negative 1. The determinant, that is an 18, by the way, believe it or not. I know that doesn't look like an 8, but it is. The determinant here is a little grosser. It's 10 times negative 11 minus negative 18 times 6. That ends up being negative 110 plus, all right, 18 times 6. Here's how I do it, really. 10 times 6 is 60. 8 times 6 is 48. 60 plus 48 is 108. That's how I'm getting there without writing anything down. You could also think of it as 6 times 20, which is 120, and then minus 12, which is 108. Or you can use a calculator. Either way, this is negative 2. And we've seen a couple times that if the determinant is negative, automatically we have a saddle. Every time the determinant is negative, you have a saddle. And yeah, and we'll see that here. But so if the determinant's negative, automatically means saddle. There is nothing else to do. We will also see this when we find the eigenvalues here in a second, because the eigenvalues are going to have, one's going to be positive, one's going to be negative. We are guaranteed based on what's happened here. Well, let's do it. So usual process, eigenvalues, eigenvectors, find C1 and C2. And then we'll talk about how to write X1 next, because I was just looking at something someone posted on Piazza. It looked like all their work was right, but they were writing X1 and X2 completely wrong. And I know they were writing it wrong because they had, for X1, they had the same eigenvalue in both spots. Their X1 was C1 e to the something times t plus C2 e to the same thing times t. They should have had different eigenvalues in both of those spots, if the eigenvalues are different, which they should be. I'll tell you what I mean when we get there. So let's see here. So eigenvalues, we're going to do the determinant, and let's just write it out. Determinant of our matrix minus lambda in the diagonal spots. 10 minus lambda, negative 18, 6, negative 11 minus lambda. Probably in the last class, or if not the last class, the class before that one, I've done my version of this problem. I know it's written somewhere in the notes. If you're looking for that, you can find it in either the last class's notes or the previous class's notes. It's probably easier than scrolling through the video. I don't know, maybe not. All right, so we're going to get 10 minus lambda times negative 11 minus lambda minus negative 18 times 6 equal to 0. When I multiply this out, I always know I'm going to get positive lambda squared, because I'm getting a negative lambda times negative lambda. So I always write that first, meaning lambda squared. And then I have a positive 11 lambda. In fact, let's be super specific distance. We'll look at this later if we need to. So that's going to give me an 11 lambda, and that's going to give me a minus 10 lambda for a total of a positive 1 a lambda. That sounded weird when I said it, but positive 1 times lambda. And then finally, negative 11 times positive 10 is negative 110. And just like it was before, 6 times 18 is still 108. So it's a positive 108. So we end up getting lambda squared plus lambda minus 2 equal to 0. Just to reinforce something I've said a couple times, notice here that the negative 2 there is the determinant, and the coefficient of lambda is the opposite of the trace. The trace was negative 1, the coefficient of lambda is positive 1. This factors as lambda plus 2 times lambda minus 1 equal to 0. So we end up getting lambda, and I am gonna say lambda 1 equal to positive 1 and lambda 2 equal to negative 2. And I would say it's a relatively standard choice to say if there's one positive, one negative, to make the positive one the first one. Doesn't actually matter that. So just like we said before, our eigenvalues are opposite signs. So yes, we have a saddle if we were trying to classify what's going on here. I keep things in frame here. Again, if you have questions, you should always feel free to ask them. Oh, I know what the problem is. It's not really a problem so much as the problem is I'd like to be more comfortable, but I need to zoom down a little bit to have everything on the screen. Cool. All right, we've got the eigenvalues. Let's find the eigenvectors. And again, I should mention there are multiple ways to do this. I know the way that typically it's being shown in class is the following. So eigenvectors, I will show it both ways. Well, I'll show one way and one the other way. So for lambda 1 equal to positive 1, we want to solve the a minus lambda I times the vector v equal to 0. Specifically, we're trying to solve for v. We want to know what that guy is. And I'm going to call it, well, yeah. So let's see here. So our matrix A was, right. Sorry. So we're doing this. Okay, so here was our matrix before. A minus lambda I is equal to 10 minus lambda, negative 18, 6, negative 11 minus lambda. So we're going to plug in lambda equal to 1. We're going to get 10 minus 1, negative 18, 6, negative 11 minus 1. I feel like I'm having a hard time saying 11. And then for v, we're going to put in variables. You can put in x1, x2, xy. I kind of like xy personally, but since we're using x1, x2, we should probably use x1, x2. Equal to, and I've forgotten this part before, it's got to be equal to 0, 0. Most of the time, unless you've got like a weird 0 somewhere, you only need to use one of these equations. What do I mean when I say one of these equations? Well, technically, this matrix equation represents a system of equations. There are two equations here. The two equations are 9x1 minus 18x2 equal to 0. And the second equation is 6x1 minus 12x2 equal to 0. You don't need both of those. Really, I'm going to say something that's not, no, it's, well, I'm going to say something that's true. Those are the same equation. They look a little bit different than each other, but really both of those equations represent the same line in the XY plane. That's why I keep saying you only need one of them, because either one you use, you'll get the same result. Here, if I solve for x1, x2, either way, I get 9x1 equal to 18x2, or x1 equal to 2x2. Same deal here. If I solve this one, I get 6x1 equal to 12x2, or x1 equal to 2x2. That's what I mean when I say both equations are the same. So that's why you only need to look at one of them, because one of them will give you everything you need as far as the eigenvector is concerned. Almost always. Sometimes you'll have something where you get zeros in the bottom row, and obviously that's not the row you want to use. Yeah, so we will say typically you can just use one of them. If for some reason you use one of them and you don't get something useful, and that occasionally happens when you have like an original matrix with a 0 in the upper right hand corner or the lower upper right hand or lower left hand corner. Sometimes one of the rows won't be helpful, but then the other row will. But most of the time, you just look at one of them and be like, cool, I'm done. Either way here, our eigenvector, which I'm going to call, if lambda 1 is 1, I'm going to call the eigenvector v1, lambda 1. There's a number of ways to think about doing this. The way I really think about it is I said, I'm going to let x2 equal 1, and then 2 times 1 is 2. So x2 is equal to 1, and then if x2 is 1, 2 times 1 is 2 for x1. Or you can say that the coefficient, the x2 is equal to the coefficient of x1, and x1 is equal to the coefficient of x2. That is another way of getting there. There are many other choices you could make. We like to make the choice where you get integers with the smallest possible values. You could have said x1 is 1 and x2 is 1/2, but that's not what we want to do because it's just not as nice. All right, let's find the other eigenvector. And now I'm going to do it the way that I personally think is better. But again, if you like doing it this way, that's totally fine. The other way for lambda 2 equal to -2, instead of solving a minus lambda I equal to 0, I say a minus lambda I times v equal to 0, we're going to solve a times v equal to lambda v. It's really the same thing. I like it better because it's the way I've always done it, but if you like doing it the other way better, that's also good. I know it doesn't look like it, but that's a 2. Maybe, sure. I think I was saying lambda and I wrote 2, or said lambda and wrote lambda. So now we're trying to solve our matrix A, which is 10, -18, 6, -11, times the thing we're trying to find, our eigenvector there, equals lambda times the thing you're trying to find, your eigenvector. What's interesting about doing it this way is your equations might not look the same, but they still are the same. Here's what I mean. So let's write down both equations, even though you only need one of them. In fact, let's write down just the first one first, and then we'll talk and we'll see what we get. So my first equation is 10 times x1 minus 18 times x2 equal to -2 times x1. It's just the first row of my matrix equation. And now, just like before, I'm going to separate x2 and x1 essentially. So I'm going to leave the -18 x2 over here. I'm going to subtract 10 x1 over there. Yep, that seems right. So -18 x2 equals -2 minus 10 is -12. And I would divide both sides by the biggest integer I can that won't give me fractions. I think that's going to be -6, or I would probably pick -6 actually. So I divide both sides by -6, I get 3x2 equal to 2x1. So my eigenvector here, again, doing the thing where I make each thing the other one's coefficient, x1 is going to equal 3, x2 is going to equal 2. x1 is going to equal 3, x2 is going to equal 2. It works, right? 3 times 2 is 6, and 2 times 3. Oh, yeah, that works. What's the only thing we can't have as an eigenvector? Everybody, tell me at once.
0.
Thank you. 0, 0. We cannot have 0, 0 as an eigenvector. Awesome. Just to point out, if we did look at equation 2, we would get the same result. Equation 2 would be 6 times x1 minus 11 times x2 equals -2 times x2. And if we isolate x1 and x2 from each other, but add 11x2 over there, I get 6x1 equal to 9x2, because -2 plus 11 is 9. And then divide both sides by 3. 6 divided by 3 is 2. 9 divided by 3 is 3. And look, that is the same equation as that, which yields the same eigenvector. So I really, really, really can't emphasize enough, you almost never have to use both equations. Once you've got one equation and you've got the eigenvector, you're done. Which is great. Okay, we've got the eigenvalues, we've got the eigenvectors. Now we have to find, if we're being asked to, if there's initial conditions, we have to find C1 and C2. Okay, this is the part where things can get a little bit messy. But let's go ahead. I like at this point to write our general solution. In fact, I don't think it's just me. I think this is what you're supposed to do. So general solution is going to be x as a vector, which is just x1 of t, x2 of t. You should just memorize this next part. You should roll off your tongue. I know it's kind of a lot, but it's not really. It's c1 e to the lambda 1 v t v1 plus the same thing with twos. c2 e to the lambda 2 t v2. I bet you've already memorized it because you've done it so many times already. And then we're plugging in the stuff we know, meaning we're plugging in lambda 1 and v1 and lambda 2 and v2. Sorry, you can't quite see that. Apologize. If something's off the screen, you can always let me know. So that's going to be, we don't know C1 and C2 yet. Lambda 1 was, I forgot which one was which. I think lambda 1 was positive 1. Yeah. Lambda 1 was positive 1 and V1 was, I don't remember either. 2, 1, thank you. And C2 e to the lambda 2 was negative 2 times t times V2, which was 3, 2. Cool. And now we're going to find C1 and C2. So plug in x1 of 0 equal to 5, x2 of 0 equal to 3. Or in other words, x1 equals 5, x2 equals 3, t equals 0. That's what we're doing. So in this equation here, and again, I should maybe write this here, x1, x2. What we're saying is x1 is 5, x2 is 3. We're trying to figure out what C1 is. Don't write e to the 0. E to the 0 is 1. You know e to the 0 is 1. So you get C1 times 2, 1 plus C2 times also e to the 0, 3, 2. This can be stranger in a nonlinear differential equation situation. If you have a different equilibrium that's not 0, then it could be a little bit dicier, but we're not there yet. All right, so I can already see what the answer is because there's an easy answer to guess at. But let's do the work anyway. So again, when you're looking at these equations, it's kind of just row by row. The first row is 5 equals C1 times 2 plus C2 times 3. And the second equation is 3 equals 1 times C1 plus 2 times C2. And then I would multiply the second equation by negative 2 and get a negative 6 equal to negative 2C1 minus 4C2, and then add those equations together. 5 plus negative 6 is negative 1. 2C1 plus negative 2C1 is 0C1. 3C2 plus negative 4C2 is negative 1C2, which, excuse me, leads me to 1 equal to C2. And then you plug that back into either one of these equations. 3 equals C1 plus 2 times 1. So C1 also equals 1, which is not very exciting. I noticed that from the get-go because I was like, oh yeah, 2 plus 3 is 5 and 1 plus 2 is 3. So if C1 and C2 are both 1, then you get that solution. But it's not always that easy to see. So I added this equation and 2 times this equation to get this. And then negative 1 equals negative 1 C2, so 1 equals C2. And then I plugged back in C2 right here because it seemed easy, although you could have picked any equation. And I have 3 equal to C1 plus 2 times 1. And then C1 has to equal 1. All right, so now how to write the solution? Well, here's how I would write the solution, which is not probably the way you're going to need to write it on your web work, but definitely the way you'd write it on a test. So x of t, I would probably actually skip this part, the x1 of t, x2 of t part. X of t is equal to C1, so just 1 times e to the t times 2, 1, plus C2, which is also 1 times e to the negative 2t times V2, which is 3, 2. Okay, so this is how you write, and I wouldn't normally write the ones there, but we're writing them just to be a little bit more explicit here. If I were then going to write what I needed to write is the answer on something like web work, x1 is again just the top row. So x1 of t is e to the t times 2 plus e to the negative 2t times 3. It's just the top row, but distributing the e to the whatever to each eigenvector. And x2 is the bottom row. x2 of t is e to the t times 1. I'm sorry, that's a t, not a 2. Sorry. Or should be a t is what I really should say because it looks like a 2. 1 e to the t, and then 2 times 1 times e to the negative 2t. So plus 2 e to the negative 2t. That is what your solution should look like. X1 is that, X2 is that. That is how we do a problem like this. Questions about any of that? Okay. Let's look at another one just because sometimes you do have weird things like this other one. So I'm going to make up one similar-ish to 5, but not exactly the same as 5. But it's the same enough. All right. Moving along. I mean, this is example number 5. Okay. Oh, sorry. There's something in the chat. There's something in the chat. Do we have to separate the? Yes. So if you look at the web work question here, right? The web work question specifically says, right, for problem. I'm sorry. Let me move that here. 1 second. Says like for problem 4, solve the initial value problem, which doesn't feel like it's saying all right. When they say solve the initial value problem, it really means do all of this. You have to find the solution, which is C1 e to the lambda 1 v1 plus C2 e to the lambda 2 v2, which means you had to have found the eigenvalues and found the eigenvectors and then did the work to find C1 and C2. That's what those 5 words mean. Do all of that is what that means. But then look how they're asking you to write the answer. Your answer is x1 of t equal to something. In this case, whatever it was. 2 e to the t plus 3 e to the negative 2t. And x2 equals something. 1 e to the t plus 2 e to the negative 2t. So yeah, we absolutely do for web work, the way it's phrased, have to separate them into the first row of equation and the second row of equation. Normally I would write my answer like this because this is pretty typical. But this is how we might have to break it apart into its 2 constituent pieces if we need to. Okay, let's look at something like, but not exactly like. Sure. Let's say we have, let's use x and y for a minute, just to change it up for once. Let's say we have dx dt equal to, sure. Let's say it's going to be 3x minus 12y, and dy dt is going to be negative 9x, sure, plus 36y. It seems annoyingly large. Yeah, oh, can you not see it? Sorry. Yes. Oh. And here's what I would observe about these equations before anything else. I would make a mental note of the fact that equation 1 is really, or the second equation here, that part there is a multiple of that part, right? If you take this equation and multiply it all by -3, you exactly get that equation. You don't have to see that, but I know that that means that lambda equals 0 is going to be one of our eigenvalues, which I know she said in class wasn't supposed to be a thing we're going to deal with, but it's clearly coming up in your homework, so we have to deal with it at least once. Again, the process is the same. So we're going to solve the initial value problem, which I feel like someone was trying to write in Piazza, but wrote IVT. And I was like, why are you talking about the intermediate value theorem? I think they meant to write IVP, not IVT. So solving this, I'm going to have to make up some numbers. It's probably going to turn out to be terrible. Let's say that x1 of 0 is equal to, how bold do I want to be here? 4, and x2 of 0 is -2. That's probably going to be awful, but sometimes numbers are awful. All right, so usual thing. You want to find the determinant of your matrix minus lambda in the diagonals. Right, it's your matrix 3, negative 12, negative 9, 36, and then in the diagonals, we subtract off a lambda. We get 3 minus lambda times 36 minus lambda minus the negative 12 times negative 9 equal to 0. All right, so negative lambda is lambda squared. Negative 36 lambda minus 3 lambda is minus 39 lambda. And 36 times 3 is, thank you, 108 again, just like 18 times 6, which makes sense because if you multiply 18 times 2 and divide 6 by 2, then you get 3 times 36, which is what we're doing. And then minus negative 12 times negative 9 is 144. This might look a little bit terrible, but check it out. You get lambda squared minus 39 lambda. 108 minus 44 is minus what, 36? Oh, maybe it is terrible. I don't know. Is this factor? I feel like I've done something wrong. Here's why I feel like I've done something wrong. I said lambda equals 0 should be a solution. Didn't I? I'm pretty sure I did. Let me make sure I didn't set this up stupidly. Times negative 3. No, it should come out right. Let's go back and so I know lambda equals 0 isn't a solution to what I've written here. So let's go back and check our work. What did I do? I don't know. Let's find out. Let's find out. 3 negative 12 negative 9 36. 3 minus lambda times 36 minus lambda minus negative 12 times 9. 9 times 12. I'm dumb. 9 times 12 is not 144. I'm sorry. I said that very confidently, so you didn't have any reason to be like, James is trying to trick us. It's 108. I was thinking of 9 times 16, which is 144. So that does not, that's just a 0 there, not a 36. So then we actually get lambda times lambda minus 39 equal to 0. So our eigenvalues are lambda equal to 0 and lambda equal to 39. And I would definitely say lambda 1 is 39 and lambda 2 is 0. Usually, if there is a positive one, we say that lambda 1 is the positive one. If there's 2 positive ones, we usually say lambda 1 is the bigger one. Again, not necessary, just typical. All right, let's do the thing. Let's find the eigenvectors. So lambda 1 equals 39. Okay, let me ask you all really, which way do we prefer to find the eigenvectors? Do we like solving a minus lambda I times the vector equals 0, or do we like solving a times the vector equals lambda times the vector? The first one. Okay, that's the way she's doing it in class. That's totally fine. It's not what I prefer, but it's not about me. Okay, so we're going to solve a minus lambda I times the vector equal to the 0 vector. I will say this way is better, especially if your eigenvalues are messy. Like if you've got things that, if your eigenvalues are like 3 plus or minus root 2, or if they're imaginary, doing it this way is probably the better way. So I will concede that fact. All right, so here we're going to get 3 minus 39 is negative 36. That's why it's also good to have this matrix written like this over here. So it's easy to just plug in your eigenvalue to it to see what you're going to get. 3 minus 39, negative 12, negative 9. 36 minus 39 is negative 3. When you do it this way, I'm using X and Y, whatever. When you do it this way, what should always happen is the 2 rows should be multiples of each other. If your eigenvalues are messy, it won't always be obvious. Like maybe the multiple is 1 plus 3i, and doing that multiplication is not easy to see, but it is true that these rows should be multiples of each other. Otherwise, the solution to the first equation won't be the same as the solution to the second equation, but we know the solutions have to be the same because you only get one eigenvector. So they are always multiples of each other, which means you only have to use one row. I would probably pick the second row here because it looks a little bit like the numbers are smaller. So let's look at negative 9 times x minus 3 times y. Oh, sorry, I forgot an important part. I always forget this part. That's why I don't like doing it this way. Equals 0, 0. So then negative 9x minus 3y equals 0. So then negative 3y equals 9x. Negative y equals 3x. And I would say that I would probably say y equals negative 3x, because honestly, we like to isolate the y thing or the x2 thing if we can. So I say that my eigenvector here is x equal to 1, y equal to negative 3. Oh, I didn't think about that. Oh well, we'll see what happens. It's nothing yet, but we'll see. All right. I'm just gonna keep going. If you have questions, stop me. And if I'm not looking up, say something. I'm just gonna keep going. All right, so let's see. So then for lambda 2 equal to 0, it might feel weird, but it's really no different than what we've done already. You're just gonna solve. In fact, it's even easier because you don't have to put in the lambda. You're just gonna solve your matrix 3 minus 0, negative 12, negative 9, 36 minus 0 times xy equal to 0, 0. Let's use the first equation. 3x minus 12y equals 0. 3x equals 12y. X equals 4y. I would not write y equals 1/4 x, even though we could. I would if we were being asked to graph the eigenlines and or the null lines, because then that's a useful piece of information to have. So here our eigenvector is going to be, you also write down the eigenvector while I take a long sip of water. All right, is it 1, 4 or 4, 1? 4, 1. Cool. Yeah, it's a lot, right? So these problems, it's the same billion steps every time, but it's the same, right? It's a lot of steps, but they are the same. Sometimes it's more terrible if the numbers are less nice, but it's always the same process. So it's really about being careful with your determinants, your numbers, making sure your signs are right, not multiplying 9 by 12 and getting 144 when you're supposed to get 108. I would imagine, I would hope, I feel like if you look at your practice exams, the numbers are not quite usually that large on the actual exams. They're more in the realm of reasonable multiplication in your head, I think. All right, so now our general solution is and I'm always going to write it out. Our general solution is xy equal to c1 e to the lambda 1t plus v1 plus c2 e to the lambda 2t v2. It's always the gist, which in this case is going to be c1 e to the lambda 1 we said was 39. Gross. Way too big. Times v1, which was 1 negative 3, plus c2 e to the lambda 2t. Lambda was 0, which means that's just going to be 1 all the time, no matter what. Times your v2, which was 4, 1. I would probably simplify this a tiny bit before I go ahead and find my particular solution. So that's equal to c1 e to the 39t times 1 negative 3 plus c2 times 4, 1. So basically, lambda equals 0 doesn't really contribute to the stability or instability at all. All right, so let's take a look. Let's go ahead and find our C1 and C2. A reminder, our initial conditions were x1 of 0 equals 4, x2 of 0 equals negative 2. Ugh, okay, we'll see. So plugging those in, I have that 4 negative 2 is equal to c1 e to the 0 times 1 negative 3 plus c2. It doesn't even matter that I've got a t equals 0 there because it's already gone because lambda 2 is equal to 0 or 1. All right, this one's probably going to be less nice. So what do I have here? I have 4 equal to c1 plus 4c2 and negative 2 equal to negative 3c1 plus c2. Has she talked about other ways to solve this? Like using the inverse matrix? It's okay if she hasn't. It's not super necessary. Sometimes it can be easier that way. It's probably not really that much easier, so I will just leave it. okay, let's do this one maybe the other way, which is I prefer elimination usually because I feel like it's usually easier, but we could also do substitution, meaning we could solve one of these for either C1 or C2 and then plug into the other one. That's not my preferred way of doing it, but it works totally fine. It's also, I would say, if you have one already that has a coefficient of 1, that's often a good opportunity to do it. Let's actually solve the second one just because it's lower. So we'll say that C2 is equal to 3C1 minus 2. And then we'll take that and we'll substitute it into the other equation. So we're going to then say that 4 equals C1 plus 4 times 3C1 minus 2. So 4 equals C1 plus 12 James, 12 C1 minus 8. So 13 gross. 13 C1 equals 8 plus 4 is 12. So C1 is 12/13. Here's why I don't like doing it this way. Now I have to plug this back into here, and I have to do 3 times 12/13 minus 2, which, okay, is not that hard, but it's not that fun. Elimination, I mean, it's the same with elimination, I guess, but you can eliminate the other way if you want. Let's go ahead and just do it. So then C2 is going to equal 3 times 12 over 13 minus 2, which let's go ahead and write it as 26 over 13. Since we know we're going to have to subtract these fractions, right? 3 times C1 minus 2. And then 3 times 12 is 36. 36/13 minus 26/13 is 10/13. All right, let's see if we can squeeze things in over here. Maybe we'll try and make it more central here. Okay, so our general solution, our particular solution is going to be this solution here. Sorry, I'm moving things around. It's going to be this solution here with your C1 and C2 plugged in. So our solution is going to be x of t, y of t equal to, so our C1 was 12/13. Sorry, I just can't get over it. It's terrible. Is 12/13 e to the 39t times 1 negative 3 plus C2, which is 10/13 for 1. There is no e to the t to write there because it's e to the 0t, and e to the 0t is just 1. Again, if you had to write these into the two separate lines, x of t would just be the first line. So it's 12/13 e to the 39t times 1 plus 10/13 times 4, or 40/13. And y of t, or x2 of t, if it's f1 and x2, is 12/13 times e to the 39t times negative 3. So I should really write negative 36/13 to make it nicer. E to the 39t plus 10/13 times 1. That's how we would write our solutions in line by line. Yeah.
Can you go for the math over there?
Which math?
The system.
Over here?
Yeah, just like
Sure. So I took this second equation and I added 3C1 to both sides so that I would have C2 by itself. So I have C2 equal to 3C1 minus 2. Then I took that C2 value and plugged it in for C2 right there. So then now this whole equation becomes this. 4 equal to C1 plus 4 times what C2 is equal to, which is 3C1 minus 2. Then we distribute the 4. So you get C1 plus 12C1 minus 8. And then bringing the 8 over here, I get plus 8. So 4 plus 8 is 12. And C1 plus 12C1 is 13C1. And then we divide by 13. And the other part over here is good? Cool. All right. That's a bad question. No, I was gonna ask something that's not a good question. Okay, so I'm pretty well convinced that none of the problems that you were asked on your homework ask you to write the solution to a system where the eigenvalues are complex. I don't, all right, yeah, for the homework. I'm not seeing, so like, I don't think we need to do that again. It was gross.
It would just be the equation of the cosine.
Yeah, it was all that jazz. Yeah. Cool, let's look at something less nice. So, meaning, okay, here's what I'm concerned about. I don't want you all to live in a place where you think your eigenvalues are always going to be so pretty. They might not be, right? You might get something like the following. I'm going to make something up. Let's see what happens. Let's say our matrix is, let's say our system is. Let's not make it too terrible, James. dx1 dt is equal to 4x1 plus x2 dx2 dt equal to, let's see, sure, that would be fine. Yeah, sure. 4x1 plus 2x2. Yeah, that's gonna be nice and terrible. There's no good reason that x1 is underlined there. I just accidentally underlined it. Sometimes I do that. All right, so let's solve it. Let's actually, I always like to start with classifying because I think classifying is a better question. It's a question we can more easily answer. So classify, you all classify. So when I say classify, you should automatically think, what do you need to do? If I say classify, what's the thing you should be doing? You could do it that way if you like doing it that way, or you could just find the eigenvalues. Either way is fine. If it were me, well, for me, I think generally finding the eigenvalues is what makes the most sense because it feels natural. We know how to classify based on the eigenvalues. So I want you all to find the eigenvalues. They're not going to be pretty. They're going to be irrational, maybe even complex. I don't think they're complex though. I do not believe it is complex. It will be irrational, but I believe what's under the square root should be positive, unless I misjudged myself.
Oh, but it actually solve it just got it.
Right, but so what does it mean to be complex? Well, you might have to use quadratic formula either way. The difference between irrational and complex is an irrational number is like the square root of 5. Right, that's an irrational number. You can't, it's a real number, but you cannot express as a fraction. Whereas a complex number is also known as an imaginary number. And where you're taking the square root of what kind of thing? Negatives. That's the difference. So this one's going to have a square root of a positive that you just can't simplify as much as you'd like to. Whereas complex would have a square root of a negative. That way I want here or not. All right, let's take a look. So again, usual thing. Determinant of 4 minus lambda, 1, 4, 2 minus lambda equals 4 minus lambda, times 2 minus lambda minus 1 times 4. Set that equal to 0. Multiply this out. Lambda squared. Minus 2 lambda minus 4 lambda is minus 6 lambda. 2 times 4 is 8. Minus 4. So you end up getting lambda squared minus 6 lambda plus 4 equal to 0. And that doesn't factor. There's nothing that there are no what's the word I'm looking for? There are no integer numbers that multiply to 4 and add to -6. But there definitely are real numbers. We're about to find them. So the real numbers are lambda equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a, which ends up being 6 plus or minus the square root of 36 minus 16 is 20 all over 2. I do recommend simplifying this as much as possible. I would point out that 20 is 4 times 5, and so the square root of 20 is the square root of 4 times the square root of 5, which is just 2 times the square root of 5, so the 6 plus or minus 2 root 5 all over 2. 6 divided by 2 is 3. 2 divided by 2 is 1. So our eigenvalues are 3 plus or minus the square root of 5. Cool. And I will point out, just because I said it, those two numbers, 3 plus root 5 and 3 minus root 5, those numbers multiply to positive 4 and add up to -6. Kind of cool. So technically, if someone says this doesn't factor, well, they mean it doesn't factor with nice integer numbers. You could totally factor this. And sometimes people talk about this. You could, if you really wanted to, factor this as lambda minus 3 plus root 5 times lambda minus 3 minus root 5. That is a true fact. This is a statement, right? That's something that you could do. All right. Same with imaginary numbers. You could also, like, once you know what lambda is equal to, lambda minus that number is how the thing factors. It's a fundamental theorem of algebra. All right, so classify. Are our eigenvalues both positive, both negative, or one of each? Both positive. 3 plus root 5 is for sure positive. And since root 5 isn't as big as 3, 3 minus root 5 is also positive. Yeah, that's all. I mean, there's nothing really more to say there than that. So yeah, so eigenvalues, lambda 1 and lambda 2 are both positive. So that means we have a what? A saddle, a sink, a source, or I would say an unstable node. So yeah, that means we have a source, also known as an unstable node. All right, so we found the eigenvalues, we classified the whole thing, and normally that's the end of the story if your eigenvalues are ugly. But let's actually do this example and see how it's not that terrible to find the eigenvalues. So the square root of 20 is equal to the square root of 4 times 5. And there's a nice property of square roots that, well, yeah, right. That if you take the square root of a product, it is the product of the square roots. And that's just 2 root 5. All right, let's find the eigen. So there's a kind of a nice thing here. You know how with like, well, actually, let's do it before I say it. Let's just see it, and then we'll talk about what we're getting here. So let's look at lambda 1 equal to the bigger eigenvalue, which is 3 plus root 5. And this is definitely the time where it is better to do it the way you want to do it anyway. To do the a minus lambda I times your eigenvector equal to 0. So a minus lambda I times your eigenvector equal to 0. All right. I remind you here that A is the matrix 4, 1, 4, 2. So we're going to do 4 minus 3 plus root 5, 1, 4, 2 minus 3 plus root 5 times x1, x2 equal to 0, 0. And this might be a case where you're like, James, those for sure are not multiples of each other. This row and this row are not, they are definitely multiples of each other. Let me simplify them a little bit just so you can kind of see it. 4 minus 3 plus root 5 is 1 minus root 5. And on the bottom here, we have 4 and 2 minus 3 plus root 5 is 2 minus 3 is negative 1 and minus root 5. I promise you, and you can check if you want to, if you multiply both of these things in this first row by negative 1 minus root 5, you will get the things in the second row. It's kind of cool. I mean, for sure here, right? 1 times negative 1 minus root 5 is negative 1 minus root 5. And 1 minus root 5 times negative 1 minus root 5 does end up being positive 4. It's negative 1 squared plus root 5 squared, which is negative 1 plus 5, which means you can use either row. And I would probably pick the first row here because it looks nicer. There's no real, there's no rhyme or reason other than I've got negatives there and a 4 there. I'd rather pick the nicer thing here and the 1 there. It just seems better. So using the first equation, 1 minus root 5 times x1 plus x2 equals 0. So sure. I would say x2 equals, I would probably not write this, negative 1 minus root 5 times x1. I would probably write x2 equals root 5 minus 1 times x1. Maybe not. I don't know. That feels kind of bad. I don't know. That feels like you should probably write it in the more correct order, which is negative 1 plus root 5. That's probably the better way to do it. So here's our eigenvector. Our eigenvector is going to be x1 is 1, x2 is negative 1 plus root 5. Okay. So here's a fun trick. Just like when eigenvalues are complex, they come in conjugate pairs, right? A plus bi and a minus bi. When eigenvalues are irrational like this, they still come in conjugate pairs, right? Our eigenvalues were 3 plus root 5 and 3 minus root 5. Watch for a second. If I change every positive to a negative, every positive root 5 to a negative root 5, and every negative root 5 to a positive root 5, so if I change all the signs, look what happens. A minus there, a minus there, a minus there. A minus becomes a plus. A minus becomes a plus. And so if I use my first row, this 1 minus root 5 becomes 1 plus root 5. If I bring this over here, it becomes minus 1 plus root 5, or minus 1 minus root 5. So my other eigenvalue for lambda 2 is really actually, sorry, my other eigenvector is super easy. It is literally just x1 is still 1 and x2 is negative 1 minus root 5. Which is kind of a really nice thing about having ugly eigenvalues, is that the eigenvalues come in pairs like this and the eigenvectors also come in pairs. Whether it's the imaginary part that you're changing the sign of or the irrational part that you're changing the sign of. It always works that way, which is kind of beautiful. Kind of. Okay. And should we find the actual solution? Well, we didn't give ourselves any initial conditions. So you can write your solution, right? Your general solution here is x1, x2 equal to c1 e to the, okay, lambda 1 was 3 plus root 5 times t times v1, which is 1 negative 1 plus root 5, plus c2 e to the lambda 2 was 3 minus root 5 times t times the eigenvector 1 negative 1 minus root 5. Not too terrible in the grand scheme of things. Definitely not as terrible as if they're complex. And then if you were given initial conditions, you could find C1 and C2. But again, they're going to be a little bit dicier because the numbers are a little bit less nice. Questions about any of that? All right, I feel like we've kind of done systems of linear differential equations to death. Not that we couldn't do more examples, but they're starting to feel like we're pretty much doing the same thing over and over again. Let me remind you of a couple things. Actually, let me ask you 3 questions at once, which I think you all should be able to answer very quickly. So I want you very quickly, the hint is that you should be able to find things easily without doing a lot of work. I want you to classify the equilibrium 0, 0 of each of the following systems. And personally, I would just write out the matrix. So instead of writing out, for example, dx1 dt equal to 3x1 plus 5x2 and dx2 dt equal to 0x1 minus 4x2, you should, I would instead just write out the matrix A equals 3, 5, 0, -4. So that's your first question. Classify that system. Here's your second one. Here's your third one. I'll give you a minute, because that's all you should need. If you're spending time finding the eigenvalues, you're doing it wrong. You shouldn't have to spend any time finding the eigenvalues. Helps. I'll remind you that for this first one, I can tell you the eigenvalues are 3 and -4. I still have like 40 seconds, so I'll wait. People at home, you should be doing this too. I mean, that's always true, right? Just a reminder though. Play the Jeopardy music. All right, that's time. So before we classify, everybody, what are the eigenvalues here in the second problem? Yeah. And what are the eigenvalues in this last one? Right. Do we need to talk about why that is, or are we all good with that? Cool, we're all good. Awesome. If anyone on Zoom wants to say more, I can. But so this first one, saddle, sink, or source. Saddle. I don't know why I'm writing in capitals, but I am. And the second one is a source. Unstable node, if you prefer. The last one is a sink. Stable node. Don't let yourself get complacent, though. If someone gave you, say, the following system, and again, I'm going to say system, and I'm going to write a matrix, right? I'm going to write the matrix A equal to, I don't know, something crazy like 5, 6, 7, 0, which is probably terrible, but oh well. No, it probably is terrible. Oh well. So if this is your matrix, well, the system that we've implied here is dx1 dt equals 5x1 plus 6x2, and dx2 dt is equal to 7x1. You could write plus 0x2, although you probably wouldn't normally. Right? So when someone writes this, they know you know that, or they expect you to know that, right? that matrix means this whole machinery here. Don't make the mistake of saying, oh, I've got a 0 there. My eigenvalues are 7 and 6 or 0 and 5, right? If you've got a 0 in one of the diagonal slots, you know nothing. You have to do all the work. So here the eigenvalues would be determinant of 5 minus lambda, 6, 7. They're probably going to be terrible because I just made up numbers. Well, let's see what we get. That's going to be 5 minus lambda times negative lambda minus 6 times 7 equal to 0. So let's see, 5 minus lambda times negative lambda is going to be lambda squared minus 5 lambda minus 42. I don't think there are numbers that multiply to 42 or negative 42 and add to negative 5. 6 and 7, 3 and 14. Nope, I don't think so. So great. Let's find the eigenvalues by using the quadratic formula. So lambda is going to be 5 and negative 5 plus or minus the square root of. I already know what the answer is. So I will point out, I know what the answer is going to be already. Because my determinant was, oh no, I'm a liar. No, I'm not a liar. I'm not a liar. What's my determinant here of this matrix? Sorry, you can't see it. The determinant is of the original matrix. So if we were calculating the determinant, we would do what times what? Right, so it would be 5 times, which is 0, minus, so what's my determinant? Almost, negative 42. And since it's the negative determinant, we know we're going to have a saddle. Let me show you why, because I think it's nice not to have to do all this work if you're just asked to classify, right? I don't want to think about this terribleness here. So here's what's going to happen. I'm going to get negative 5 squared here, which is going to be 25. Now watch. I'm going to have minus 4 times 1 times negative 42. All divided by 2. Since my determinant is negative, I end up adding stuff here because it's always a minus 4 times A times C. But since C is negative, your minus 4 times your C becomes a positive thing. So watch this for a second. I have 5 plus or minus the square root of 25 plus something. And what I want you to really know is that the square root of 25 plus something, that's bigger than 5. And so if you take 5 and add that, and take 5 and subtract that, one of them will always end up being positive, one of them will always end up being negative. And it wouldn't have mattered if that was 5 or if that was negative 5. Because negative 5 plus that's going to be positive. Negative 5 minus that's certainly going to be negative. So it's really, really always true. If your determinant is ever negative, you automatically have to have a saddle. Because the eigenvalues will be real, because the inside to the square root will be positive, and the inside to the square root will be bigger than whatever the square of that is, so that you end up getting both sides. You can't get both being positive and both being negative. You have to get one of each. Not so. So let me. So the determinant is of the original matrix. So this is right here. This is the determinant of A minus lambda I. Product of that minus product of that. But the determinant of a 2x2 matrix in general is always, and the way I'm always going to say it is the product of the diagonals minus the product of the off diagonals, which is what we calculated here. So in this case, that was 0 times 5 minus 6 times 7, which ended up being negative 42. So if you happen to notice that your determinant of your original matrix is negative, then your eigenvalues will always be opposite sign, which means you'll always have a saddle. Now, if you're using the quadratic formula, you can also see it by, well, if this constant term here, right, if that's negative, that's the same thing because that is your determinant right there. So that's another way to see it. 4 times 42, who cares? I mean, I do, but okay, whatever. Whatever that is, that's certainly going to be positive and negative. So we have a saddle. Which is neat. I think that's neat. All right, I don't think you've started talking about compartment models in class yet. But definitely section 11.2 of your homework is all compartment models. So maybe we should talk about it for a minute because we'll probably start talking about it tomorrow. And let's think about, so timeline, basically we're doing all this until Thanksgiving, right? And then you have your test on everything up through chapter 11 or whatever, 11 on your homework, 10 in the book. On November 29th, the Wednesday. And then after that, the Friday, maybe even the Monday before. And then the week after that, which is the first week of December, which is the last week of classes, right? Let's see. How much class do we have left? So it's always good to think about how much more there is left to do. So you can kind of plan ahead. So let's see. So we've got this week. I assume on Wednesday and Friday, you'll talk about compartment models or more differential equation stuff. Right. Monday of next week. I don't know what you're doing next week. Monday and Wednesday, I assume you'll have class. I wouldn't be surprised if she canceled class on Wednesday or did remote class on Wednesday. Right. The following week, Monday is before your midterm 2. You have review. Okay. Okay. Sure. Wednesday will be the actual exam on the November 29th. And then you have class on December 1st. And then 4th, 6th, and 8th, and then finals. So after your second midterm, there's 4 classes left. And this is typically where we cover most of the chapter 12 stuff, which is all the probability garbage that nobody likes. And we always tack on at the end of this class for God knows what reason. So even though it might not feel great, I'm probably going to start talking about the chapter 12 stuff before you take your second midterm, because it's probably good to get you ready for it. But before that, we should talk about compartment models for a second. So we've got 7 minutes left. Or 9 minutes left. Can I tell time? Sure. We've got some amount of time between 5 and 10 minutes left. Let's look at a compartment model situation here. I wish I had a better example on me, but yeah, I really wish I did actually. I know. Let me grab something. Oh, there's something in the chat here. Sure. I don't, so, well, not, oh yeah, that's right, nonlinear, but so the compartment models actually come before the nonlinear. So section 11.2 is the compartment model stuff, and then section 11.3 is nonlinear. So actually, you know what, you make a good point. Let's actually do a nonlinear example, just because the compartment models are really still systems of linear differential equations that you're already pretty familiar with. Let's go ahead and talk about one differential equation, nonlinear, just to kind of see what that even means. So let's look at a system of non-linear differential equations. So example, a non-linear. Oh, yep, you would like to see maybe, and also maybe, yep, good point. Non-linear system of differential equations. So basically non-linear just means you have something other than x1 to the first and x2 to the first. Maybe you have a square, maybe you have them multiplied together, right? Just something other than the usual something times x1 plus something times x2, and then something times x1 plus something times x2. So for example, you could have the differential equation dx1 dt equal to 3x1 minus x1 squared minus x2, and dx2 dt equal to x1 minus x2. And this is a non-linear system of differential equations because you got an x1 squared. Now, what's interesting here is you're going to typically have more than one equilibrium. 0, 0, although still an equilibrium here, right? If you plug in 0 for x1 and 0 for x2, both differential equations, both derivatives are still equal to 0, but you're probably going to get other ones as well. So let's find them. So let's find the equilibria. So we're trying to, this is gonna sound familiar, I think. Yeah, we're trying to solve two systems of equations equal to 0 simultaneously. A lot like when we were finding the critical points of functions of two variables and setting the partial with respect to x equal to 0 and the partial with respect to y equal to 0 and finding solutions to both simultaneously. That's what we're doing here. So I would probably start off with the second one. So I'm going to have x1 minus x2 equal to 0 or x1 equal to x2. Great. Now I'm going to plug that into the first differential equation so I can actually get something. So I have 3x1 minus x1 squared minus, I'm going to plug in x1 for x2. All right, 3x1 minus x1 is 2x1. So I have 2x1 minus x1 squared equal to 0. If I factor out an x1, I get x1 times 2 minus x1 equal to 0. So my solutions here are x1 equal to 0, x1 equal to 2. And since x1 and x2 have to be the same, otherwise this equation won't equal 0, then we're going to get our equilibria are going to be x1, x2 either equal to 0 and 0 or 2 and 2. Let's check. Clearly the second equation is equal to 0 regardless of which pair of points. 0 minus 0 is 0, 2 minus 2 is 0. If we plug 0, 0 into the first equation, it's also pretty obvious that we get 0 minus 0 minus 0, which is 0. If we plug in 2, 2, we get 3 times 2, which is 6, minus 2 squared, which is 4, and 6 minus 4 is 2, and then minus 2 is 0. So yeah, they both work. So both of these are equilibria. Now, here's where things get a little bit interesting. To determine the stability of an equilibrium, we want to be able to look at the matrix. But the problem is, you only have like local stability, meaning around the equilibrium, maybe you have a spiral, maybe you have a saddle, maybe you have a sink or source. But if you go too far away from that, you've got totally other things happening. And so what we're going to do is we're going to look at essentially the matrix that's like what would be the system of linear differential equations around that point of equilibrium. Here's what I mean. You need a sip of water, don't you? So to determine, oh my gosh, it's all coming back. To determine the stability, we use a linearization. But it's not as bad as it sounds. Because so the thing is, we really only care about like the coefficients of x and y. So normally if you were trying to do a linearization, you would be like z equals f of x naught, y naught, plus the partial with x times x minus x naught, plus the partial of y times y minus y naught. It'd be terrible. But we only really care about those partials, because those are the coefficients of x and y. Right, because those right when you're doing the matrix and the previous stuff we've always been doing, it's always just the coefficients of x and y that are in your matrix. That's all we're going to do now. And the coefficients of x and y, or x1 and x2, are just the partial derivatives of each function with respect to each variable. So here's what we're going to do. We're going to use the Jacobian matrix. And here's what it's equal to. It's equal to, I need to go back and label one thing real quick here, but I'll fix it. It's equal to the partial derivative of f with respect to x1. What's f, you might ask? Good question, since I didn't tell you. This is f of x1, x2. This is g of x1, x2. F is just what the first derivative is equal to. G is what the derivative of the second variable is equal to. Sorry, I said first derivative. I should have said the derivative of the first variable. So the Jacobian here is the partial derivative of that with respect to x1, the partial derivative of that with respect to x2, and then we do the same thing for the second function. Del g del x1 del g del x2. So in this particular example, the Jacobian is going to equal, so we take the derivative of this first thing with respect to x1, you're gonna get 3 minus 2x1. You take the derivative of this first thing, let's start the x2, you're gonna get 0 minus 0 minus 1. Take the derivative with respect to x1 of the second thing, you're gonna get 1. And derivative with respect to x1, x2 of the second thing, you're gonna get -1. So there's your Jacobian. I'm gonna write it again because I've run out of room on the paper and I want to write it again because I want everybody to see on the section. So here's our system one more time. I know we're almost out of time here, but let me just, I promise you, I'm almost done. And I think you want to see this. So we've got all this. And again, we're calling this first one f of x1 comma x2, the second one g of x1 comma x2. Our Jacobian, which we just found, is 3 minus 2x1, -1, 1, -1. So now let's look at the Jacobian at the point 0, 0. Okay, so at the point 0, 0, our Jacobian is going to be 3, -1, 1, -1. And now you find the eigenvalues to determine what the stability is. I will point out here that the determinant of this matrix is equal to -3 minus -1, which is -2, which is negative. So we know we have a saddle. If you really care, the eigenvalues are equal to 1 plus or minus √3. But again, I don't actually really care. If someone said classify, they're not asking you to necessarily find the eigenvalues. They're just saying that's one way you could do it. Because the eigenvalues are opposite values or because the determinant is negative. Right. And then at the other point, 2, 2, our we get 3 minus 4, which is -1, -1, 1, -1. And there, our eigenvalues are complex, I think. Let's find out. So we have the determinant. I know we're out of time. If you need to leave, you can, but I really want you to see this. So I apologize for taking more time than I have, but I'm going to do it anyway. Solving that, we get -1 minus lambda times -1 minus lambda minus -1 equal to 0. Multiplying this out, we get lambda squared plus lambda plus lambda plus 1 plus 1. Is that right, James? Yeah, okay, that's right. Plus 2 equal to 0. And using the quadratic theorem, you get quadratic formula, -2 plus or minus the square root of 4 minus 4 times 2 all over 2, which ends up being -2 plus or minus the square root of -4 over 2. So -2 plus or minus 2i, or -1 plus or minus I. Okay. -1 plus or minus I. The eigenvalues are complex, meaning we have a spiral. Is my spiral stable, unstable, or neutral? Good question. And I feel like we haven't talked enough about spirals now that at the 3 minutes past class being over. I guess Thursday we can have more stuff. This one is stable. And stable because the real part is negative. Just like if the eigenvalues are real and they're both negative, it's a stable node. So whether it's a negative real eigenvalue or an imaginary eigenvalue with a negative real part, the real part being negative is what leads to stability. The real part being positive leads to instability, right? If it was +2 plus or minus I, or my eigenvalues were just 2 and 3, those both being positive or those both having a positive real part lead to instability. Okay, I should stop talking.